Good morning. I hope there's some oxygen in the rest of the room and that there will be some oxygen left at the end of my talk. I do not intend to breathe at all. I'm Julian, currently at NYU. I've been to a couple of different places. I grew up like 500 meters away from here. And then I was a student of Jacek, amongst others, from my undergrad. In Lund, I went to Sussex to study biologically inspired robotics. Then I changed sex and went to Essex. And I've also been to various places, Switzerland, Copenhagen, currently working in New York. I basically started out thinking that I was going to do philosophy because, I was going to become a philosopher because I hated maths very much, with a vengeance. And I couldn't deal with it. So I studied philosophy, but I ran out of ideas, I guess. Or I guess I was too impatient because basically philosophy moves very, very, very slowly. I wanted to understand the mind. Philosophy wasn't making much progress there. So I sort of moved towards artificial intelligence, thinking that if I am to understand the mind, I will need to build the mind first. And then when I started my PhD, I was thinking I was going to do biologically inspired robotics, so evolutionary robotics. The problem with robotics is that robotics is also very, very slow. As some people know here, robots sort of break down all the time and they need a lot of time to program and stuff like this. And I was too impatient for that as well. So I switched to computer games. Thinking that computer games not only were they fun to play, but they were like excellent test beds for AI, and you can run them like 1,000 times real time and so on, and basically face many of the same challenges as you do in robotics, at least the interesting ones of the challenges. And that was correct. But along the way, I also found out that you could do a lot more with games than just play them. And your AI can do a lot more in the context of games than just playing them. And that's basically what I do. And I'm going to tell you a little bit about some stuff I've done, some stuff that other people have done. And the takeaway message, if you want to leave already now, is that you can use AI for many, many more things in the games than just playing them. And there are many interesting AI problems there. So let's start with artificial intelligence. This is how I think of it. No, that's actually not how I think of artificial intelligence. I think of it as simply as making computers able to do things which currently only humans can do. Actually, I'm not sure about the English of this sentence, but you get the gist of it. And if we think of AI applied to games, what do humans do with games? Audience participation. What do humans do with games? Play them. Yes, that's number one. Everybody always says play them first. And then people say? Create them. What else?
Find Easter eggs.
Find Easter eggs. True. That's good. Anything else? Huh? Sell them.
Provide commentary.
Provide commentary.
Play.
Cheat. Complain. That's very good. There's a couple of new ones over there that I haven't actually, that people don't usually come up with. So basically, I usually categorize them as play them, study them, build content for them, and design and develop them. I don't know what cheating fits in here, but you could see it as part of the development phase where you're doing automatic game testing, or where you're doing game testing. But we have people playing games, obviously, in very many different ways, and very many different people play games these days. It's a lot broader than it used to be. You also have all these people doing game studies, studying games from humanistic perspectives, social science perspectives, and so on, and try to find out things about them. Games are very interesting to study. People build content for them, put it online. There's all these enormous amounts of Minecraft worlds and StarCraft maps and so on that people have built, hobbyists have built online. And of course, they design and develop them. So what I'm thinking is that AI can be used, could be used in all these roles and many more, probably. However, this is how people think of it. This is John McCarthy playing chess against his computer program back in the 60s when the world was in black and white and there were only white men. This is state-of-the-art AI. people had this idea that chess was sort of the Drosophila of AI. I mean, if we work in AI, we should work in chess, because chess embodies what's important, again, about human reasoning. Then we came to the 90s. There was color in the world. And Garry Kasparov here was beaten by IBM's Deep Blue. And people's idea that chess was sort of the epitome of intelligence really took quite a bit of a beating, because basically Deep Blue was essentially just minimax search with a lot of interesting hand-coded heuristic functions. And then we come to 2016. We have Google DeepMind playing Go and winning Go, winning a number of matches of the game of Go, which was sort of the last remaining grand challenge board game against one of the best players in the world. Go doesn't really have a formal championship as is. All right, so here we have people working on playing board games and thinking that this is sort of this is what you do with AI when it comes to games. My take on it is this, that basically playing board games is a very, very limiting both in terms of domains, because board games are easy to sort of conceptualize and they're easy to sort of encode. They're so easy you can even sometimes prove things about them. Crazy. But they're really, really a very, very, classic board games are a very, very small part of the wide space of games. And learning to play them and sort of, coming up with algorithms that can play them is just a very, very small part of everything, all kinds of tasks you can do with AI. So basically what I do most of the time is finding new points outside this little yellow dot here inside the blue dot, and trying to find new things you can do with AI in games, and then trying to do those. It's a lot of fun. So let's start from the beginning. We can use AI as testbeds or games as testbeds and benchmarks for AI, but not only with board games, and certainly not only classical board games, but also video games. Here we have a couple of video games that are quite different to each other in different ways. I'm sure most of you recognize Super Mario Bros. This isn't actually Super Mario Bros. You see up here. It's the Mario AI benchmark, which is an AI benchmark based on Infinite Mario Bros., which is a clone of Super Mario Bros. Made by Notch, who later made Minecraft before he got famous. I was going to publish a paper with him, but then he dropped out and didn't do anything more about it, so I sort of regret not pushing that further. Would have been cool. But so it's a version of Super Mario Bros., which you can interface your AI to. This looks like a generic FPS. It sort of is. It's called Unreal Tournament 2004. You run around, you shoot things. This is a fairly generic driving game called Torx, and this is StarCraft. Anyone here do not know what StarCraft is? Hey, 1, 2, great. StarCraft is the national sport of Korea. Well, not officially, but it's true that if you check into a hotel room in Korea and turn on the TV, chances are you'll find one of the several cable TV channels that mostly broadcast StarCraft matches, which I think is fantastic. I mean, it's a way more interesting game than football. It's a two-player asymmetric real-time strategy game where you build bases, harvest resources, attack your enemy, and obliterate them. And it's by far the hardest AI challenge I know of. It is that anyone is seriously considering as an AI challenge. You need to basically reason on a lot of different levels. You need to sort of handle your micromanage your troops. You need to sort of tactically move them around. You need to decide which resource to harvest, when, and how often. You need to plan the building of your bases and have areas of planning at different levels of strategy. People, I mean, in Korea in particular, StarCraft pros are like treated as pop stars and have like, big entourages, play matches in front of thousands of people in sold-out arenas. I think that's a pretty nice civilization. It's an extremely hard game. What these games have in common is that in the main conferences in our fields, the IEEE Computational Intelligence and Games Conference and the Artificial Intelligence and Interactive Digital Entertainment field. We have competitions based on these 4 games that have been running for several years, and where people submit their best bots to try to sort of beat each other in these games. So let's look at what it can look like. Let's start with a case of like having training AI, so somehow building AI to build a specific game. This is the first time we ran the Mario AI benchmark, or the Mario AI competition in 2009. We had this submission. Here we have Mario running around, jumping, playing fairly well, right? Could you play this well? No. I love showing this video. It sort of puts people in a trance. We were sort of sad when we saw it because basically we thought that we had built this really, really nice benchmark. And then now someone comes around and submits this thing. And we thought this was a fairly hard AI problem. But you couldn't do that. Turns out that this guy really does really well. He won the first year's competition. And I mean, even more sadly, do you know what the main algorithm here is? Any guess? No, but yeah, it doesn't have it's not adversarial, so min-max wouldn't do it, but it's a star search in state space. So he basically does a very, very simple planning forward and he just tries to get to the edge of the screen at all times. So we thought about this and we decided the problem was actually not actually with the game. The problem was that all the levels were so linear so that if you moved in the same direction, you could actually win. Now, what if we came up with these sort of dead ends where you basically have to backtrack and find another path sometimes because you don't know which path you're taking? Made the whole thing a lot more interesting. Here we have the same algorithm running into one of these dead ends. To get out of here, we will need to go back and jump up here. And obviously, he can't see that far ahead. Basically, the algorithm just times out. It explores a lot of those sort of local paths here, but it can't see far enough in the future. Second year we ran the competition. We had this interesting thing called Realm, which is an evolutionary algorithm that designs rule sets that decides where to explore and then uses a star at the bottom level to implement this exploration, which is already a lot more interesting than it was before. So already in the space of 2 years, you could see that we evolve the benchmark a bit, and people evolve the submissions to come up with something more interesting and capable. However, these Mario, just as an aside here, basically, we realized pretty quickly that the best competitors did not look very much like humans at all. So we set up a secondary track of the competition, which was essentially a Turing test. So basically trying to figure out how can people come up with AIs that play in a human-like manner. So this particular one here is a Bayesian network trained on a number of human play traces, so it can play in what looks to humans like how a human would play the game on a number of unseen levels, which is a lot of applications. If you want to test your levels, if you want to test your game, or if you want to demonstrate new levels or demonstrate the game mechanics to a player, for example, then this is very useful. All right. We found a couple of we've basically validated this across a couple of different games that there are these signs of humanity. Things such as hesitating before you take an action, doing a couple of uncalled for actions that seemingly do not have any kind of intention behind them. Trying and failing, I mean, it's a very important thing. However, we've been running these competitions for a while. Super Mario Bros, StarCraft, car racing, etc. And one thing that becomes clear after a bit is that when you run the competition, the first few times people try to submit very generic AI solutions that might be learning from input and trying to adapt as much as possible. But as you keep posing the same challenge over and over, what happens naturally is that people overfit. So in the car racing competition, which has been running in one form or another for like 8 years now or something, or 9, what we're seeing is a very high degree of domain-specific solutions. People essentially submit hacks. Actually, the AI content of what people submit has been going down. Originally, you had these sort of reinforcement learning algorithms trying to learn to drive in general. And now we're seeing things where like all of the driving is actually hard-coded, and you have a very, very small learning or search component somewhere in there that sort of slightly adapts it to the particular track you're driving on. And this is sort of uninteresting. From an AI point, it's pretty uninteresting. Another thing is that, I mean, the best car racing controller cannot play Super Mario Bros. Or StarCraft. I mean, there's not even a way to connect it to the other game. Which is also points to that something is wrong here from an AI perspective. I mean, a human who could only play one game wouldn't, or a human who could only do one task wouldn't really be a human. So, I mean, a core part of intelligence is being able to do more than one thing. So, we can take this nice example. I usually tell everybody to never ever show an equation on a slide. I think it's like very bad form, show an equation on a slide. People fall asleep. But I'm making an exception here because I think it's important. This is Shane Legg, my old friend and colleague, who defined general intelligence as such. The general intelligence of a policy or an agent is the sum of its reward of this policy over all possible environments weighted by the inverse simplicity of the environment. What does this mean? Basically, like how intelligent you are is basically how would you do on all possible problems. But we take the simpler problems, the ones that are more fundamental in a sense, to be more important as we weigh this together. I think this makes a lot of sense. Lots of people think this made a lot of sense. Shane Legg did a PhD in this, and then he went on to start Google DeepMind. So I guess this equation has a lot of sort of influence in the world today, or will have. It has two problems. One problem is that you have to sum over all possible environments, which of course takes longer than a lifetime of the universe, etc. And it's sort of impractical. The other problem is that this thing here is the Kolmogorov complexity of the environment, which is incomputable, also sort of impractical. So clearly, we cannot just measure general intelligence this way. We'll have to approximate it somehow. So that's one of the main reasons we created what we call the general video game playing competition. The general video game playing competition is a competition where people submit controllers. Currently, we have a Java interface. We've been thinking a lot about adding support for other programming languages. Once upon a time, this was implemented in Python, but the Java solution is 100 times faster. So we're not going back to Python. People submit the best controllers, trained on we have a number of games currently, 60 games available to sort of test your controller on. And then they get submitted and get scored playing a number of unseen games. So they don't know what they're going to play. There are new games every time. And we developed a language for this called the Video Game Description Language, which is, we started thinking about like all these arcade games from the late 70s, early 80s, and what they have in common, and came up with what was intended at least to be a simple way of expressing a game that has a two-dimensional movement and graphical logics, meaning that most effects in the world are determined by various sprites interacting in some way. So here's an example. This game here has a sprite set that's basically the ontology. This is what exists in the world. It has a level mapping this level description file. These are walls. You can see a W. Oh, W is implicit, but basically G here maps to goal. The plus here maps to a key, for example. And then the interaction set, which is basically, these are the core rules. When something that's movable collides with a wall, then you stop, for example. If an avatar collides with the enemy, then yeah, the avatar dies and you lose a point, for example. And finally here is like, this is defines when you win or lose the game. And we basically, I think most things that people ever implemented on the Commodore 64 could be described in some form, some simplification of it in this language. So here's an example. This is a human playing our implementation of some core gameplay elements of the element of Zelda. The guy comes and picks up a key. He tries to avoid the spiders too much, kills another spider, wins this particular level. Of course, all the games come with different levels, so we have at least 5 levels for each game. Here's a random player taking random actions. He's not very good. So how do you actually play this? It turns out that most of the actually good controllers get submitted here are based on some version of Monte Carlo tree search. I'm not sure how many of you know what it is, Monte Carlo tree search? Some of you? It is essentially, it's a new black, essentially. It's therefore the dog is slide here. It has, it's a tree search algorithm that uses stochastic rollouts, taking random actions until the end, and estimates the value of various actions that way, and builds a tree of possible actions. It is very, very, very generic, and it's essentially the only thing that works if you have basically can make no assumptions about your problem. So here's a version, and Monte Carlo tree search-like algorithm called open loop expectimax search that plays Zelda and behaves a bit weirdly. This was the winner, by the way, of the 2014 competition here, and eventually wins. Now, this is not so impressive in itself. This is just a simple, stupid game where you run around in 2D and kill spiders and pick up keys, like you would at home. But let's take exactly the same controllers, exactly the same human. He's one of my PhD students, playing a version of Space Invaders. So this is also a very, very simple game description. Well, I mean, you all know Space Invaders, the old arcade game. And it's all about basically timing your shots right and avoiding getting bombed. It gets harder in later levels. Hey, yeah, we can move forward here. You have a random player playing this game not very well. He will eventually lose because he's just shooting at random. And you have the same algorithm, again, with no knowledge of which game it's playing, playing this game and winning in far shorter time than a human would. Yeah, as soon as he's done with, I think at some point he will stop and sort of actually, yeah, now he gets serious about things. We also have a version, this is Boulderdash. Any of you remember Boulderdash? Quite a few people, yeah? Fantastic game of the 80s. You run around, you collect diamonds, you try to avoid getting trapped beneath falling boulders or getting a boulder falling on your head. Don't let out these weird monsters, they will kill you, and so on. I'm not going to go through all of this in the interest of time because it takes some time to play through it. Let's say that the random player here does not do very well. He's doing random. The open loop expectimax tree search player is actually not, he sometimes wins. This particular time that we got for the video, he doesn't win. Whatever, doesn't win. But it does a lot better than most of the other solutions. It's a fairly hard problem. I mean, playing Boulderdash would be simple if you could feed it all the particulars of the game, but here we don't. We just basically feed it a representation of all the objects in the screen, and then basically it has to figure out what to do. We don't tell the agent what the objects mean or whether they're desirable or edible or something. It has to find out for itself, which is what makes it hard and what makes it interesting. So here's like the results from the 2014 competition, where you see one interesting thing is that, one interesting thing, as you can see from the results here, is that it's non-transitive. Different algorithms are differently good at win different games. And there's currently a lot of work among the sort of expanding community of people working on this problem at coming up with algorithm selection methods or hyperheuristic methods to try to select good algorithms for playing individual games. So it's like early on figure out what kind of game it's playing and adapt the strategy in some way to do that well. Right, let's move on from playing games. Let's go to developing games. This is perhaps somewhat a bit of a caricature of modern game development. But in fact is that I have students that want to go into game development and they have this idea that, oh, I want to be the designer, I have so many ideas. Actually, when I worked at University of Copenhagen, one of the main conclusions of a working group on increasing employability among our students was that we need to get rid of all the ID people that have a lot of ideas and want to be fantastic designers. Because actually, the truth of it all is that this is how you start out. The truth of it all is that also that game development is an extremely labor-intensive process that has people. Developing a AAA game, so a big budget game that goes into multiple markets, might take 100 people 3 years to do or something like this, or more than 100 people, several hundred people, might cost hundreds of millions of dollars. So somehow, AI is supposed to make us all unemployed. That's a great promise, right? So what can we actually do here in terms of game development? Well, one thing you could do, obviously, is to try to automate some of the content generation. So these are a couple of examples from back in the days, mostly, of different games. I don't know if you recognize Elite up here, the space shooter game. Dwarf Fortress, Spelunky over here is a fantastic game, Civilization. What these games have in common is that they all in some way depend on procedural content generation. The game worlds are created by the game as you play the game. Or at least some aspects of the game world. This is done partly to reduce memory usage, but mostly not have to manually assign all the content and basically make it so that, Spelunky, for example, every time you play it, you get completely new levels, which is great. It brings a completely different gameplay than if you would have played a traditional platform like Super Mario Bros., where you can memorize the shape of each level. Here you have to actually learn how to play the game. So this has been used in the game industry in particular roles for a long time. What I'm doing is trying to one of the things I'm doing is trying to widen the scope of what you can do. What can be generated? Can everything be generated in a game? How can we do that? How can we do that effectively? Can we save development time and effort? Can we actually make these generation algorithms more creative than humans in some way? Because humans are not very creative. They tend to basically copy each other mostly. Can we create endless games? So basically, if I play Grand Theft Auto, it looks like a fantastic, huge, living world. But actually, it's only a few square kilometers. In the real world here, I could go out and steal a car and then learn to drive it and then basically drive 5 hours in some random direction. And there would still be people there would still be an environment, there would still be things happening. Why don't we have that in games? Also, why don't we have games that adapt to the player, that decides that, hey, we figure out that you don't like the shooting very much, but you like the puzzle solving and the whatever dating aspect of this game. Here's some interesting content for you. And you didn't know that you also liked the racing aspect of the game. There we go. Here's some stuff you might like. Finally, you could also study game design by formalizing it. As a computer scientist, you don't know a process before you've implemented an algorithm that can do it for you. So in the same way, you don't understand game design until you've developed an algorithm that can design games for you. At least that's what I think. So something we've been doing a lot is search-based PCG. We call it search-based procedural content generation. What it actually means in most cases is using evolutionary computation to evolve content. The main issues here is like levels or game worlds or characters or something. Main issues here is how to represent the content so that you can search a space of content effectively, and how to evaluate the quality of content. How to evaluate the quality of the content is sort of AI complete in itself, because it basically means that I need to automatically tell how good this Super Mario Bros. Level is. Is it 0.6 or 0.7? And it's very hard to do that if you're not a human. But hey, it wouldn't be any fun if it wasn't hard. So let's take as a simple example, Super Mario Bros. This is actually something that Steve, who was here earlier, did for his PhD. He basically came up with this representation of Super Mario Bros. As a number of slices, of horizontal slices you see here. And he went through all of the original levels. He figured out that 90-something% of them could be represented with only 25 different slices. So this is you see here, this is, we can call this slice 0. It's a slice 0 again. Here's slice 1 because I have a question mark. Slice 0 again, and here will be slice 2, etc. So there you can represent a whole platform game level just as a simple string. Very convenient. What he did then was basically identifying a number of larger patterns that could be instantiated in different ways. So this is a 3-way pattern where you can go below these question marks and on above the first row or at the very top. And usually they have some sort of reward that's hard to get at the very top. And this could be instantiated in a lot of different ways. So here's some example of trying to evolving Super Mario Bros. Levels to include as many patterns as possible. You get levels which have a lot of local structure and local meaning, but they sort of lack the sort of overall meaning and the sort of pedagogical aspect of real Super Mario Bros. Levels, which are really masterclasses in game design, the levels for the first game. I mean, if you have some time over, you should go back and play the first Super Mario Bros. Game. It is so amazingly designed. Anyway, so we went on later on with trying to encode a different, more global structure. We've also been working on, for example, StarCraft maps this way, come up with balanced StarCraft maps. This is not my work, trying to, looking at how you can generate rules for completely new games. This is Cameron Brown, evolving board games. He defined a simple sort of board game description language looking like this. And then he came up with this evolutionary process where he takes existing board games, selects parents from them. I'm basically showing this example because I really, really like this graph. I also like the result. Do crossover between different board games, mutate them, check the rules, are they well-formed? If not, throw them away. Baptize the games, check if they're playing. If they're too slow to play, throw them away. Otherwise, try to tune a policy to play them well. See if they're drawish, if then throw it away. Are they inbred, if then throw it away. Otherwise, no, score them using a very, very complex scoring function based on automatic playout, and then put them back into the population. And these runs were, of course, this is a very, very complex process. It took him weeks for each game, or each evolutionary run. One of the results is the game Yavalath. It is, you can buy it in a store. It has really good reviews on Board Game Geek. And people say that this is a very nice and simple board game with some new rule elements that, that people really appreciate playing. It says over here on the side that it's designed by Cameron Brown and Ludi, which is a system. But that's actually false. I mean, Ludi designed the game. Cameron Brown just designed Ludi. The big question is, why is Ludi not getting any of the money? But I think this is really a great example of when this process can actually really, really work. Designing complete games this way. Final thing before I just move to conclusion. Yes, we can have the AI design things, but sometimes humans are actually useful as well. And the human in collaboration with AI would reasonably be the best choice for developing something. As, by the way, these days, the best chess is not played by humans and not played by computers, but it's something called hybrid chess or centaur chess, where humans play together with computers. You have a chess computer, you have a human that makes a move and uses a chess computer to evaluate the different ideas for moves. And this is the best chess, because basically you can have the human intuition and the computer infallibility together, which is, I think that's really cool. So here's a mobile game called Cut the Rope. I don't know if anyone of you have played it. It was really popular a couple of years ago. You're supposed to sort of move this little candy around and then cut various ropes at the right time to feed this little frog or whatever it is. Here's our here's something we call the Ropossum, which is our AI-assisted editing tool for Cut the Rope. What you see here is that you can automatically generate levels that are playable by just pressing a button. And then you can design them. You can sort of move things around just as you would in any sort of design program. You can put like various bumpers, ropes, and so on, these cushions that you help you blow the candy in various ways. So it's a normal level editor. The company doing this were pretty awesome, let us use the graphics for doing this. And then you can check the playability. Then it tries to sort of search for the playability of the game, figure out how long time it takes to play. It shows you at the top of the screen now which actions you need to take to win the game as it plays it for you. You can also tell you how hard this particular level is, how many different sort of actions you need to take. We're also thinking about like, yeah, you review the 2 trees of possible actions you can make, you can do. The game playing AI is a mess in here, but yeah. You can take some of your designed levels, fix those, and tell the level editor or level generator to regenerate the rest, give you new stuff for it. So basically, I like these and these parts. Regenerate this part of the level. Or, you know, here's a beautiful thing that I like, but it's not solvable. Fix it for me, essentially. So it has a lot of, a lot of different options for this. And this is something, this sort of having the AI as your sidekick, having him as your design assistant that does stuff for you, gives you feedback, tells you what your design is like, points to things you didn't think about, does all the boring stuff for you, is something that I think will be very, very important. We're trying to do this now for the general video game AI framework, so it works not just for one game, but for any game in this language. Right, I'm out of time. I'm just mentioning was working in adaptive games, measuring player experience, optimizing, for example, Super Mario Bros. Levels to sort of optimize various aspects of measured playing experience. Hey, we know how you play. Now we can make something that's maximally fun and minimally frustrating, or maybe the other way around. So to sum this up, what can games do for AI? I think these are really the best test beds for AI. I mean, if you work in AI, why don't you work in video games? I mean, other applications are sort of boring. And I think they're also the best possible test of general intelligence. Also, I think that, you know, real intelligence, you can't have real intelligence if you can't have fun. So basically, in the end, AI will need to have the capacity to have fun. What can AI do for games? Well, there's a whole bunch of things. I mean, we're working on generating complete games, which requires generating game content, which requires being able to evaluate game content quality and test it, which requires modeling player preference and player style, which requires learning to play any kind of game. So having learning algorithms can learn to play any arbitrary game. So there's enough work to do here, really, but a lot of possibilities. Right, that's it for me.